Hello teacher, my name is Yun. I'm in the manager in aerospace engineering, and I'm taking the problem one in numerical method.
My name is Nguyễn Ngọc Anh Duy. I'm learning aerospace engineering and I'm problem two in the numerical project.
Hello teacher, today I will explain with you the problem one which I have made it. So when I read the problems that I will give inside them 10 randomly data points. So I will use the interpolation method. The reason why I use the cubic spline interpolations because the Lagrange and Newton they have some disadvantages about really big data and they really impossible to solve when too much data. And I choose the cubic spline because they much easier to use and they have effectiveness. So at first I give 6 data points first. Which one I have highlighted in the yellow. So when I give 6 first data points, I will create this some functions through these 6 data points by using the natural cubic spline. Here, I will create the coefficients to create the piecewise function go through these 6 points. And when I graph this 6 function in this graph, I see the cubic functions will have 2 roots in derivations, and they will create a local minimum and local maximum when they equal 0. So actually, I added 2 more data points on the graph inside my data point. So it will be 2 of these, the local minimum and local maximum on the piecewise. So the center point is the problems of us because when we create a center point, the delta of the function must be equals 0, uh, which means uh, it's really hard to find out. So I will choose it to be specific one, and it's be the x minus 15 powered by 3. Um, and when they graph inside, they the set point function they go separately with the other ones, and they don't have anything to connect together. So I will give one more data point to connect the uh, all of the function before with the set point functions together by using graphic cubic spline, and I give them some conditions, which mean the derivations of the 6 old function data point and the derivation of set points when they are in the fifth in the 14th. So I will have the conditions of them to connect together, and there's our graph. You see, they go smoothly together and connect them together inside one graph. So that's our data point. Thank you for listening.
I'll talk about the second problem. So in this question, we will choose the Lotka-Volterra model. A little bit introduction about this model. The Lotka-Volterra predation equations is also known as prey-predator model, were independently proposed by Alfred James Lotka in 1925 and Victor Volterra in 1926. This is a pair of first-order nonlinear differential equations that are frequently used to describe the dynamics of biological systems in which a predator and its prey interact. So we will use the rabbit for prey and fox for the predator. Let y1 is the number of rabbit and y2 is the number of fox. We assume that the amount of grass is enough for the rabbit to eat forever. The number of rabbits born in a unit of time is proportional to the population of the rabbits themselves due to this equation. So the solution of it is y1 equal to a constant multiplied for e power at, where a is the coefficient depend on the environment. So as a result, we can see that the rabbit populations are always growing dramatically, but in reality, the fox will eat the rabbit, and therefore, this equation is obviously untrue. More rabbits are consumed as there are more fox. The quantity of rabbit consumed must also be proportionate to their whole population. So, this equation should be rewritten as this equation. So without the rabbit, there would be a food shortage and fox would become fewer in number at a rate corresponding to their own population. The number of deaths per unit of time increases with population is following to this equation, and the solution of it is y2 equal to a constant multiplied for e power minus ct. So We can see that the fox survived and continued to consume rabbit to flesh support the colony. The fox's ability to reproduce increases as there are more bunnies to feed them. So we can rewrite the above equations as following this formula. So from those equations, the simplest version is the following pairs of ODEs due to these two equations, where A is the growth rate of prey, B is the rate at which predators destroy prey, C is the death rate of the predators, and D is the rate at which predators increase by consuming prey. So to solve these two equations, we will use the Euler's method to solve them. So let's talk about the Euler method. If we are given the equation this, like these two equations, then we can consider the Euler's method with step size h. We can have the x0 is equal to a, and then x1 is equal to x0 plus h, etc. to xk equal to x0 plus hk. So define the sequence. We can have these two equations where k is more or equal to 0. Then we will have the approximation y of xk is approximate to yk. So about the mathematical formulation, we will assume that the initial rabbit population is 10 and the initial population of foxes is 2. Therefore, we will have the first equation here where we assume that the A is equal to 2, B is 0.5, C is 1, and D is 0.5. So we let step size h is equal to 0.05. Then we use this MATLAB code. We will have a plotting like this. So we can see that the fox population grows a little more slowly as the number of rabbits rises. The fact that there are more foxes means that the number of rabbits cannot expand exponentially, instead increasing, weakening, and finally declining. When the quantity of rabbits surges, so does the rate at which foxes proliferate. The number of foxes also decreases over time as a result of the drop in rabbit populations, which first harms them by depriving them of food. The threat is lessened, the fox is diminished, and the rabbits are reborn. So the process of birth and death keeps on. So we can plot the rabbit population and the fox population due to time by using a function in MATLAB, and then we will have these two plotting. So we can see that it is a periodic. Next, about the result, we can see that the data we gathered were consistent in the literature we read before starting the problem-solving process, and to our first approximation, the fox predation, which surely relied on rabbits for food, was the only thing keeping the rabbit population in control. The Lotka-Volterra model has the amazing property that the solutions are always periodic. In our case, we were only able to extend the model to 20 times, but by doing so, we would be able to observe the periodicity of this model. The population always resume the cycle and go back to their original values. The periodic solutions of nonlinear models are uncommon, and determining the period's duration is the challenging part of finding the solution of the predator-prey equations. So, with a basic understanding of this equation, people may modify its parameters to affect the environment in ways that help them achieve their objective, like impact on the ecosystem's self-stabilizing and self-balancing mechanism, such as the development of artificial ecosystem, pastures from grazing animals, and agricultural land. However, because these ecosystems are frequently unstable, individuals must inject more energy in the form of work, fuel, and fertilizer in order to maintain this artificial ecosystem. Or we can forecast the population of each species and then reveal the interaction effects among different competing species. In conclusion, the modeling predator-prey dynamics has historically relied heavily on the Lotka-Volterra equations. Although the non-trivial solution to the system may be unrealistic, it is simple to alter that it more closely resembles than occurs in nature. So we can solve this equation by use finite difference techniques can do numerically solve the model itself. That is our that is our presentation. Thanks for listening.